Alrighty, howdy folks. Section 2 of chapter 16 is what we will cover today, and it's about line integrals. In physics 2, there's something about, I vaguely remember something like charge, I think, or current when flowing through a certain wire in a direction. There's a line integral involved in that scenario. I apologize for not remembering that, but for sure I know it appears there, okay? All right, so what's with this line integrals? Back in Cal 1, you remember just integral over definite integrals over an interval like integral a to b f of x dx? So these line integrals are actually a sort of extension of that, okay? For example, we can extend this concept to integration over a curve, and we call those extensions onto a curve as line integrals. The book says something interesting. It says, I think they should have called it curve integrals because it's not just a line. The line could be a curve. I like that, but unfortunately or fortunately, they call these things line integrals, and we'll stick to that convention. Okay, we extend this concept to integration over a curve C. In the sense, we could have a function that's being integrated not just on an interval a to b. Integral a to b would be a sort of a horizontal line segment, you can think of it, right? Like that, right? What if it's not just a horizontal segment? Instead, it is some kind of a curve in the xy plane. Could we integrate a function f of xy along that curve? Look at how mathematicians think about these kinds of things. And sure enough, physicists and other engineers make use of these things. Okay, so we need to learn this. So to be able to do something like this, what we have to do is learn how to express that curve in a parametric form. But the truth is we already know about it. In Cal 2, we learned about parametric curves. Basically, what's a parametric curve? If you have a curve and you can write the x as some function of t and y as a function of t. I think in calculus 2, they were careful to say x equals some f of t, y equals g of t. But then there's a maturity that we have reached by the time we got to Cal 3, and we don't say, hey, when I say x equals x of t, that's okay, man. Don't, what's that American, who's that? Bart Simpson, right? Don't have a cow, man, or something like that, he says. For the life of me, I never understood what that meant. So if somebody comes and says x equals x of t, how can x be of x of t, man? So maybe I should go Bart and say, don't have a cow. Just understand that x is basically some function of t. Okay, similarly, y is a function of t. And there has to be some restrictions for the t itself. So a less than or equal to t less than or equal to b. Cool. So we first need to express the curve as a parametric curve. Or we can write that curve as a vector equation. This is just another way of writing exactly the same thing, okay? R of t is x of t I plus y of t j. Okay, so the vector form of that curve. So we need to start with the definition. So what is a proper definition of this? If f is defined on a smooth curve C as given above, so f must be defined on that curve. That seems like a reasonable request, right? F better be defined on a smooth curve if you are planning to evaluate the integral of that function on that curve, along that curve. Just as when we say integrate along an interval AB, the function better be defined on that interval AB. And not only that, we expect continuity of the function on that interval. So here, as you can see, f is defined on a smooth curve C. Smoothness here is first derivative continuous. Okay, that's what smoothness refers to, meaning if you take the first derivative at a certain point, based on the left-hand side, it must be the same as the first derivative on the right-hand side. Okay, based on the right-hand side points. So the curve has to be smooth. And then the line integral of f along C is given by integral over or integral of f of xy over this curve C ds. That's an interesting one. This is basically a Riemann sum version we are talking about. So this is not such a useful formula. I put it there for the sake of completeness. But there are other kinds of things that we will talk about which are much more useful. However, what is this provided this limit exists? So this is just the Riemann sum version of it. Now, however, we still need to understand what in the world is ds is. ds represents the differential arc length of the curve C. Differential arc length of curve C. What do I mean by that? Okay, shucks, I don't have a picture of it. But let's say there's some curve, some parabolic curve, let's say. Now, it has a starting point where t equals a. Now I'm looking at the parametric form of it. At t equals a is the starting point and ending point is t equals b. So from t equals a to some delta t, there is a itty bitty small piece of that curve, right? And that small itty bitty piece of curve has a certain length. Would you agree? And that length of that curve is what we are calling as ds, the differential length. Okay, fine. But how in the world do we find that differential length, arc length? Well, if you remember, in Calculus 2, we talked about arc lengths of parametric curves. And there was a formula. The length of a parametric curve from a to b, from a less than or equal to t less than or equal to b, is integral a to b square root of dx dt square plus dy dt square evaluated with respect to t. This was a formula. So what do we mean by ds? ds means instead of going from a to b, we are going from some t equals a, t equals some value, to t equals whatever that value plus delta t, a small change in t. Okay, so that's what we are talking about. And it turns out that ds dt, ds would be simply, we can write like this rather. Okay, ds dt is what this square root of thing would be. If I multiply both sides by dt, then we have ds is basically this quantity. All right. And so f of x comma y, now we are no longer keeping it in terms of x and y, but we are writing it in form of the parameter t. So f of x of t comma y of t, and ds is replaced by this, because after all, ds represents the differential arc length. And that differential arc length is actually given by this formula. Okay, this you sort of have to remember, memorize. So that's why I put it in a outline. I put it in a box. Okay, I'll illustrate all of this with quite a few examples. First, let's start with something straightforward. Integral over some curve of the quantity x over y ds. And the curve is already given to us in a nice parametric form. X equals t cubed, y is t to the 4, and t lies between 1 and 2. Okay. So to me, it looks like all we need to do is just plug and chug. Our objective is to evaluate something like the left-hand side, right? This one is like this. So we'll say that's equal to the right-hand side, and we'll use this formula on the right-hand side to evaluate the left-hand side. That's our strategy. Okay. Can we quickly realize what is what? Do we know what f of x comma y is? Clear. X over y. Cool. Do we know what a is? A to b. Oh, 1 to 2. Okay, a is 1. B equals 2. Would you agree? Do we have x and y? Yeah, x is a function of t, y is a function of t. Yep. Cool. Armed with all of this, could we now say f of xy is x over y, but x is t cubed, y is t to the 4th, so that's t cubed over t to the 4. That's 1 over t. A is 1, b equals 2, like I said. Cool. What else? We definitely need to figure the square root thing out, which means we definitely need to figure out what dx dt and dy dt are, and then compute that. Given x equals t cubed, dx dt is clearly 3t square. Y equals t to the 4 means dy dt is 4t cubed, right? Okay, that's what I said here. Now, let's figure out that big long thing. Integral square root of dx dt is going just plug and chug, and we get 9t to the 4 plus 16t to the 6. Can I factor out a t to the 4? Yep. And when I factor a t to the 4, and can I pull that outside of the square root? In that case, would that become t to the 4 inside the square root? Would it become t square on the outside? Okay. And what are we left with? We factored out a t to the 4, remember. So we have a 9 plus 16t square. So all of this square root thing just reduced to this happened to be equal to this. Cool. We already said x over y ds is nothing but 1 to 2, t cube over t to the 4, t square. That part is the x over y part, t cube over t to the 4. And ds is all of this. And so if I simplify it, it becomes t times square root of 9 plus 16 t square dt. Simple integral, straightforward integral. Any ideas how to do this? U substitution. If you say u equals 9 plus 16 t square, du is going to be 32t dt, and so go from that. And it turns out, if you evaluate this, you get this quantity. Okay? Is that it? Yep, that's it. Cool. All right, let's move on. Let's look at another problem. We have some function of x, y. Cool. ds, that's fine. C is the line segment from 20 to 54. So they didn't give us a parametric form of the curve. They said it's a line segment from this to this. So what does that mean? That means it's up to us to figure out what the parametric form of that line segment is. Do we know how to find a parametric form of a line segment from a certain point to another point? Well, recall that a simple way of finding a line equation, parametric equation of a line segment from P1 to P2, position vector P1 to position vector P2, is to simply say R of t is nothing but P1 times 1 minus t plus P2 times t, and the parameter varies goes from 0 to 1. How do you know this, man? How does... Well, simple. Check this out. This line segment is a directed line segment from specifically point P1 to another point P2, right? So that means when t takes on a value of 0, we must be at the initial point P1. Let me repeat that. When t takes on a value of 0, we must be at P1. Likewise, when t takes on a value of 1, we better be at that other point P2. Now, does this accomplish that? Let's check. Let's plug 0 for t. Then what happens? 1 minus 0 is 1. And P1 times 1 is P1. Plus P2 times 0. Oh, this disappears. And so we end up getting P1. So t equals 0, of course, gives us P1, which is what we want. Similarly, when t equals 1, this goes to 0 because 1 minus 1 is 0. And P2 times t becomes P2 times 1. So we get P2. So this works. In fact, we talked about this long time back itself. Okay. All right. So what does that mean? That means our curve, in this case, P1 happens to be this position vector is 2, 0. That point 2, 0 coordinates. I'm writing it as a vector, position vector, times 1 minus t. Similarly, the other point is 5, 4 t times t. And what can we combine these two vectors? Can we add these two vectors? Yeah, multiply this. So you get 2 minus 2t plus 0. 2 minus 2t comma 0. That's what happens to this. And this becomes 5t comma 4t. Add the x components comma some of the y components. When you do that, we get 2 minus 2t plus 5t and 0 plus 4t, right? And if I simplify that, this simply becomes 2 plus 3t comma 4t. So we had to figure out the parametric form of the given curve. And we have done that. We also have the bounds on t. Okay. Now, based on this vector function, we can also say, oh, you mean x equals 2 plus 3t and y is 4t. So we need to have this ability to go from our version to the xy version for a curve. Depending on the context, we will use one or the other. Okay. So we say that x equals 2 plus 3t and y is 4t. All right. Now what? So that means given our f of xy to be x e to the y, that integrand, we now need to convert that into f of x of t comma y of t. Basically what that means is replace x with whatever x is a function of as a function of t is. So for x I'm plugging in 2 plus 3t and for y I'm plugging in 4t based on this. Okay, remember that. Once you get the vector function, once you write the curve as in a parametric form, you know what x of t would be and y of t would be for that curve. And you substitute those x and y for your f of xy. Okay, it's almost like, if I say, hey, boys and girls, f of x is equal to x squared. What is f of 3? You plug a value of 3 wherever you see x. It's kind of like that. So f of x comma y is you plug these 2 plus 3t for x and 4t for y. So f of xy now has been expressed as a function of t. Good. What else? We also need this dx dt the quantity square plus dy dt the quantity square under the square root. Dx dt is just 3, dy dt is 4. So that's why I have this. And that's a nice Pythagorean numbers. So those are 3 and 4 are nice Pythagorean numbers. So that's 5. What else? Yeah, just matter of plug and chug. Cool. So what does this give us? So 2 plus 5 can be yanked outside. 2 plus 3t e to the 4t. That's integration by parts. So if you do some integration by parts, I didn't bother to show you all of that. You get the final answer to be this. Cool. All right. Next. Integral over a curve, fine. E to the x dx. Huh. They don't even have a ds this time. Is that an issue? Nah, not at all. Okay, so we can still deal with it just as if this is some kind of a ds. Okay, and the arc of the curve is x equals y cube. Whoa. They didn't even put it in the parametric form. Instead, they express the curve in terms of x as a function of y. And they didn't even tell us, obviously, t values. So it's up to us to find the t values. Write this in a parametric form. Write this curve as a parametric form and also figure out the bounds on t. Take a look at it. Can you figure out? Can you write this curve as a parametric curve? Truth is, it's not really that difficult. For example, we are given that the curve is x equals y cube, right? So the trick at this time is to say y equals t. Cool. When you have something like x equals y cube, we say y equals t. So x would become t cube. You see that? So that's what we are going to do. We'll say y is t and x is equal to t cube. Okay, what else? -1, -1 to 1 to 1. So that means the y value is y value of -1 to a y value of 1. Why am I talking about y? Why am I focusing on only on the y coordinate being -1 to 1? That is because we know we set y equals t, right? We set y equals t. So that means whatever the y values are, which is -1 to 1, t must be -1 to 1. In order to get the bounds on t, I'm focusing only on the y coordinate of the initial and terminal points. Excuse me. That is the key here. Okay, let me talk about just a little more. Needless to say, if I had x equals y square, what should I have done? Same thing. Y equals t is what I would have said. And x would be t square. Cool. What if I were to reverse things? What if I had y equals x cube? What should I do? Well, I'm sure you guessed. Make x equals t, and so y would be t cube in that context. Right? That's all there is to it, folks. Okay. So to express x equal, we can choose y so that x equals t cube with -1 less than or equal to t. And the rest of it is fairly straightforward. F of xy is e to the x, but for x, let's plug in t cube. And dx, notice, this is somewhat straightforward. Because we don't have a ds, all we need to do is say dx. Well, given x to be t cubed, dx is 3t squared dt. So, is this problem as simple as -1 to 1 e to the t cube? Yep, it is. Right? Okay, the question is, how do you integrate e to the t cube 3t squared dt? Well, substitution. If you say u equals t cubed, then du is 3t squared dt, right? So this just becomes integral e to the u du, which is e to the u, which is e to the t cube. So evaluated that. That's it. Simple. So notice in all these problems that I have done so far, we are given f of xy and a curve over a curve. You need to evaluate the integral over a curve of some f of xy ds. Sometimes the ds could simply be dx, and we are given the curve. We may have been given the parametric form of it, or we may not have. Okay, let me get a drink. My throat is absolutely dry. Uh-oh, I'm sorry. I had this muted, so let me go back and talk about this. Okay, so definition. Let f be a continuous vector field defined on a smooth curve C given by vector function r of t such that t lies between a and b. F is a continuous vector field. That's interesting, isn't it? So far we had some function of xy, but now apparently we are looking at some vector field f. And the question is, can you actually integrate a vector field along a curve? The answer is yes, you can. Well, and that vector field, integral of a vector field over a curve is defined as f dotted with dr, where r is the parametric form of the curve expressed in a vector form, okay, as a vector function. In other words, we have to evaluate that f as f of r of t, the composite function, dotted with r prime of t dt. What? Where'd you get that from, man? Well, would you agree that dr dt is the same as r prime of t? So multiply both sides by dt. So dr is nothing but r prime of t dt. That's all we did here. So this is another very interesting one. So here we are talking about integrating a vector field over a curve. Cool. And this is the way to do it. Note, one more thing. A slightly different concept here. Curve C has a certain orientation. What do we mean by that? In the sense that it has a starting point A and a terminal point B. Right? Now, what if we were to switch the endpoints? If the endpoints are switched, we refer to the curve as negative C. What do you mean by a curve negative C? Well, it simply means if you thought of the orientation going from one point to another point as positive, then reversing the direction is considered to be a negative curve. All right. And the reason you need that is when it comes to these integrals, integral negative c on the reverse part of the curve is actually negative of the regular orientation of the integral over the regular curve. Okay, that's the relationship. This should not come as a surprise because did you know that integral a to b of f of x dx is the same as negative of integral b to a of f of x dx? Right? You can check that for yourself. Suppose you take an integral of x square from 1 to 2. If you switch from 1 to 2 to 2 to 1, you better multiply that by a negative and say that's equal to negative integral 2 to 1 x squared dx. That's precisely what they're saying here. And that this you need to know this for a certain reason, and I'll show you that reason. Oh, I can show you that reason only in the next section. Okay. Keep this in mind though. Evaluate the line integral f dot dr where c is given by the vector function. So more or less straightforward. There's a reason why I'm saying more or less straightforward. So vector field, f is a vector field, and it's given by xi plus yj plus xyk. And the curve is given by this, t goes from 0 to pi. Right? So this is the thing, and it looks like this. So that means we need to know the right, we'll make use of the right hand side to figure out the left hand side. Cool. A and B, clearly 0 and pi. All right. F of R of t. What do we do about that? F as a function of x, y, z is xi plus yj plus xyk. What do we mean by f of R of t if R of t happens to be this guy? Well, here is the idea. Would you agree that basically what this is saying is x of t is cosine t, y of t is sine t, and z of t is t. X, y, and z. That's what it is saying. Okay, so solution. Based on the vector function, we say that x is cosine t, y is sine t, and z is t. So come back here and plug for x each one of those things. X comma y comma xy. That's nothing but, what did I do when I wrote this way? I wrote this in the vector form, right? Instead of ijk, I just wrote it in the using the angle brackets. Why am I doing that? Because I need to take the dot product pretty soon. Okay, that's the reason. Okay, now what did I do? I simply replaced x with a cosine t, and this y with sine t, and this z component, which is of this vector force field, the vector field is xy, which is cosine t times sine t. What happened to the z, man? Well, somehow this vector field doesn't care. Doesn't have a z in it. It has the vector field as a z component in it, but those components are not dependent on the z coordinate. Please be absolutely clear about that. Let me repeat that. If the question is, hey, what happened to z? Z, nothing happened to z. This vector field is such that it has x, y, and z components. However, none of the components depends on the z coordinate. That's the idea. Okay, cool. And R of t, we know, Can we figure out r prime of t? That's because, notice, we needed f of r of t. That's what we did. And we now need r prime of t. So knowing r of t, all we need to do is differentiate each component with respect to t. And that's what we did. Derivative cosine t is negative sine t, derivative sine t is cosine t, derivative t is 1. So we got this. And what next? Just plug and chug. Integral 0 to b. I went ahead and figured out f dot r of r prime of t. Remember how to find the dot product of two vectors? The like components, multiply the like components and then add up the whole thing. Cosine t times negative sine t plus sine t times cosine t plus cosine t sine t times 1. That's what I did. And when you do that, these two add up to 0 and we're left with a cosine t sine t. Right? That whole thing's just cosine t sine t, and we need to integrate that with respect to t. How do you do this? You can do substitution. U equals sine t, du equals cosine t dt. Or, yeah, I like trig. So I wrote this sine t cosine t as 1/2 of sine of 2t, because sine 2t is 2 sine t cosine t. And so that's just negative 1/4 cosine 2t evaluated from 0 to pi is just 0. Bummer. We did all of this work and the integral turned out to be just 0. Yeah, that's okay. Did you get this? Ladies and gentlemen, that concludes our lecture on 16.2. Where are you?